So let's pick up where we left off in class discussing the extent of the nuclear radius. We were doing a derivation where we had a low energy alpha particle coming in, okay, and being stopped by a large Z nucleus, gold, and it slows down, turns around, and its kinetic is converted to potential, and you had the equations up there. If you did things correctly, all right, you should have gotten a value for the radius around 5 times 10 to the negative 14th meters. Okay, and so that fits in line with what we talked about last year. We said the radius of a nucleus or nuclear level is around 10 to the negative 15th meters, or a femtometer. This derivation is very effective. It gave us our first real estimate of nuclear sizes, and it was a key development in atomic physics. So if we look at the radii of other nuclei, going from hydrogen to, let's say, uranium, you might expect that the nucleus would get bigger and bigger and bigger as we pile on more nucleons within there. It turns out that that's true to a certain extent, but it's not as it doesn't grow as quickly as one might expect. Okay, so it doesn't change appreciably with atomic mass A. So through careful experiments, we're not going to derive this equation. We have an equation. This is in your reference tables. It gives the nuclear radius r as a function of A. And so just without further ado, we'll just give it as it's some baseline radius times the atomic mass to the 1/3 power, or the cube root of A. Okay, so we can see because of the cube root that the radius is not going to grow as fast as one might. R naught is given as 1.2 times 10 to the negative 15th meters, so that's kind of in line with what we saw there, or we can call it 1.2 femtometers. Okay, femto means 10 to the negative 15th, and I'm not sure if that's sometimes called a fermion, not a fermion, but a Fermi, for Enrico Fermi, who worked at this scale. So we can apply this to uranium-238, fairly straightforward. The radius of that would be equal to R naught A to the 1/3, okay, which would be R naught 238, that's the atomic mass. We don't want the number to the 1/3. If you take the cube root of that, that turns out to be essentially 6 times the baseline radius. Okay, so you can do the math from there, but it's about 7.2 times 10 to the negative 15th meters. All right, so it's a pretty straightforward calculation. What we would want to do, use it more, is a more interesting calculation, and that's to give you the idea of the density of the nucleus. Okay, so in the nucleus you got all these nucleons packed into an exceedingly small space. We might expect that to be a fairly high density, but how high? And we can also show that it's independent of the atomic number. In other words, the density of a helium nucleus is essentially the same as that of a uranium nucleus, even though the uranium nucleus is much, much bigger, which kind of makes sense because they're made of the same material. Okay, so it's a nice little derivation. So let's start off with the definition of density. Density is mass divided by volume. Okay, so let's take each of those pieces. The mass of the nucleus is going to be equal to its atomic mass multiplied by the mass of 1 AMU. So I'll just call that U. Okay, let's not confuse that with gold. So it's A times U, and U we know is around, I don't remember off the top of my head, but let's say 1.66 times 10 to the negative 27th kilograms. It might be 1.67, but that's not going to really be a major factor here. All right, how about volume? Well, we're going to treat the nucleus as a sphere of sorts, so the volume is going to be 4/3 pi r cubed. Okay, so let's put it together. And I'm going to spill over into the space here. So our density is going to be equal to the mass, A times a U, all over 4/3 pi. Now we need the nuclear radius. Well, how do we calculate the nuclear radius based on the atomic mass? Well, we have this equation right here. So that's R naught A to the 1/3, and the whole thing has to be cubed. Okay, so let's simplify. So we have A times U all over, let's bring the 3/4, flip, copy, change, flip, over pi, R naught cubed, and A to the 1/3 cubed is A. All right, so we can see that the atomic mass cancels out, and we're left with rho equals 3 over 4 pi atomic mass unit times r naught cubed. Okay, so we can plug in the numbers. 1.66 times 10 to the negative 27 kilograms divided by 4 pi, and our r naught before was 1.2 times 10 to the negative 15th meters quantity cubed. You can start seeing, wow, that denominator is a really tiny value, especially with the cubed, and we work it out, we get a whopping 2.3 times 10 to the 17th kilograms per meter cubed. That is the essentially most dense object that we can talk about to have any real meaning. There are some stars at the end of them that they're called neutron stars that have essentially the same density. That is a lot, to say the least. Okay, and again, it's independent. So it says calculate for, well, you fill in the blank. It really doesn't matter there. We could even do it for hydrogen, which is essentially saying that the density of a proton or neutron is essentially that, which makes sense. Okay, so let's finish up by looking at two other aspects of the nucleus. One is looking at another independent way of determining the nuclear extent, this time using high energy, not low energy, electrons. Okay, we're talking, let's say, 400 MeV, so very, very high energy. Remember alpha particles in the previous problem were around 4 MeV, so we're at 100 times. Now, why would we do electrons? Well, first of all, electrons, if they have to have high energy to penetrate, to get through the electrons that are surrounding that nucleus, let's say. I don't know if we would have an ion of it where there would be no electrons. Secondly, it's not going to be repelled by the nucleus. Okay, you can say, well, it'll be attracted, but what can happen is if we got the electrons moving really, really fast, they're going to have a de Broglie wavelength, right, lambda, and then when they encounter that nucleus, I'll just call that a big positive sign, the right wavelength will diffract around it and give us a classic single slit interference pattern. And based on the angle that it diffracts, this first minimum, we can use that angle and knowledge of its wavelength to determine what the size of this object is, which we'll call right now d. Okay, so it's a clever little way of determining nuclear size by using diffraction. So what you have here is intensity of diffracted electrons when it's fired at a particular nucleus and the diffraction angle. Okay, in other words, if this is 0 degrees right there, we have an angle that goes along there. And if you look closer, we see a peak like we'd expect at 0 degrees, and then it drops off, and then it rises again and drops off, and then this theta right here is the minimum, our first minimum. Okay, and in this case, let's say it corresponds to 35 degrees. This is, by the way, a carbon nucleus, carbon 12. So for carbon 12, that angle would be 35 degrees. All right, so let's calculate what the radius must be for an angle of 35 degrees. Well, from diffraction, you see up there, we have that the size of the sine of theta equals, since we're treating it as a spherical barrier, the nucleus that is, 1.22 lambda all over this d that we're talking about, the diameter. Okay, so we know that the angle of the minimum occurs through experiment is 35 degrees. Now all we have to do is get the lab wavelength. That's a de Broglie wavelength. So de Broglie wavelength, recall, is Planck's constant divided by the momentum of the electron. We know the energy, so let's relate momentum to energy. We're going to use, and I'm not going to do the side thing, but we know that one way of looking at momentum besides 1/2 mv squared is we can use the relativistic equation, which says that E equals P times C. Therefore, P is equal to E over C. In other words, we can say that the wavelength is equal to HC all over the E. All right, so now we can plug in numbers. I'm not going to do the conversions. I'm going to use for my reference tables a value for HC that is 1.24 times 10 to the 3 EV times a nanometer, very convenient little unit, and our energy we said earlier is 400 MeV, so I'm going to convert that times 10 to the 6th eV. All right, I divide those two numbers, and I convert the nanometers to meters, and I get a wavelength, lambda equals 3.1 times 10 to the negative 15th meters. That's good. That's roughly the same size that we expect of the nucleus. All right, now we can apply our diffraction equation. So we can say sine of 35 equals 1.22 times 3.1 times 10 to the negative 15th meters divided by d. Solve for d, okay, and we get 5.4 times 10 to the negative 15th. So therefore our r, which is half of that, would be around 3 times 10 to the negative 15th meters for a carbon nucleus. Okay, so our r naught is 1.2, carbon nucleus is roughly 12 times that, cube root of 12 is 2-ish, so we can see that's consistent with that idea. So a neat little application of single slit diffraction, in this case around a barrier rather than through an opening. So it's a nice review for topics we've learned before. If you have any questions on that derivation, something that came up, don't be afraid to ask. Okay, so the last thing I want to talk about is something that happened much later in the 20th century. This was around the 1960s, I believe. We started probing nuclei with very high energy alpha particles. Instead of MeV, we might get, instead of 4 MeV, we might get into energies that are on the order of 20, 30, 40 MeV. So this graph right here, the one on the left, is the classic Geiger Marsden graph that shows how the distribution of angle changes with the amount of events changes with angle. This graph on the right is looking at the counts once again, but now on the y-axis is the amount of energy with the incoming, let's say, alpha particles. And we see that for low energies, it follows that curve very nicely. Then at a certain threshold, around 25 to 30 MeV, it deviates noticeably. Okay? And that deviation revealed something very important about the nucleus. Okay? What did it reveal? Well, this is getting ahead of ourselves a little bit. But essentially, the electrons have so much energy that they're overcoming that Coulomb barrier that would repel them, and they're penetrating deeper into the nucleus. And then they're encountering another force that is causing them to scatter with a different distribution of angles. And this is our first evidence of the strong nuclear force, which we'll have more to say in the next chapter. Okay, but our evidence for this other force comes from this deviation in the curve because, again, those alpha particles are coming with so much energy that they're able to penetrate more than they normally would be. And so the Coulomb repulsion reveals, that's not enough to explain this. We have another force. Okay, so that is it for our discussions on nuclear structure. Our next steps will be looking at stability and decays.